So starting a new energy level seems to be kind of a deal breaker where it just doesn't seem to have that, that trend of going up. So those are the two exceptions that we have to know. We looked it up on the books data earlier. This trend with the nitrogen-oxygen, so the group 5 and 6 families in the periodic table, that goes all the way to the 4th row, where AS, arsenic, has a higher ionization energy than selenium does. And then the next one down, finally the atoms are big enough where you don't have so much of a pronounced repulsion that finally they follow the trend. But it takes you to the 5th row where the group 5 and 6 are actually following the trend. Anybody have any questions about that? All right. It's kind of a boring lesson, but it's important. There's lots of questions, and as we go through some of the other things, you're going to see that idea will come up again. So there's several things that kind of tie together here. Now, fortunately, when we go down a family on the periodic table, there's no exceptions. It just goes, it kind of falls right in line that when atoms are getting bigger, the ionization energy is going down. It becomes more and more easy to remove an electron. That idea of a shielding effect is really in play now because you're piling one energy level on top of the other ones. And so those outer electrons, they don't have the attraction for the nucleus like the inner ones do because the inner ones can feel it more. So that's ionization energy. Fortunately, that one is the longest. So now, as we go through each property from here, they'll get shorter and shorter every time. We good with that one? The next property is electron affinity. And I know that was in the reading assignment too. Do you know what the word affinity means? What do you have an affinity for? I have an affinity for chocolate. You have an affinity for phones. Yes? Your phones. Mitchell, maybe not you, but other people your age. So yeah, some people have an affinity for fast cars. Some have an affinity for fast boats, you know, that kind of thing. So we all have our own thing. Now atoms have a thing for electrons, of course. So the electron affinity is going to measure how an atom feels about gaining an electron, how attracted the atom is to an electron. When you look at this, now this was what the reading quiz said about which one is the least consistent. Oh my goodness, this is inconsistent. They're going up and down, even within a row. Man, we got some very positive, some very negative. There's a lot of jumping. I know there's quite a bit on here. One thing I would like to say before you get too much into just writing down what's written up here, notice that in this one case of this property, the 0 is not on the bottom. All the other properties have all positive values, but this one has some positive and some negative values. So I'm just going to highlight the 0 line for electron affinity. It looks like that. Some elements are above, meaning they have a positive electron affinity. Some elements are below, meaning they have a negative electron affinity. Now, if you take a look at what the definition is, the energy change when an atom gains an electron? So a negative electron affinity, like these are, that means the atom is giving off energy when it gains an electron. Oh, it likes that. Nature tends to want to get rid of some of its energy. So this just at the bottom tells us what it means to be positive or negative. Negative electron affinity means it's stable when it becomes -1. And a positive one means it is not more stable. It is not excited at all about taking an electron. The most negative electron affinities are who? That should be no surprise. These have the highest attraction for electrons to gain an electron, because gaining one electron means that they can achieve a noble gas configuration. So they'll be very stable if they can gain an electron. What two families, there's two full families that are resistant to gaining an electron? Can you tell from up here? What two families would not want to gain an electron? What's one of them, Archita? The noble gases are one of them. Here they are. Helium, neon, argon. All of them positive. They're all pretty much the same positive value too. They don't want to gain an electron. Who else? There's one even higher than the noble gases, which is a surprise. Can you name that family? What's that family called? Beryllium, calcium, magnesium. The alkaline earth. The alkaline earth. The first family is the alkali metals, and then the second one is the alkaline earth. What's going on with that alkaline earth? Man, they really don't want to gain an electron. Well, you can see where they are. What's going on with their electrons? They have just filled an S sublevel. Now they're going to have to put one electron into a P. Start a new sublevel. And I had just mentioned before that I think it was on, yeah, this one. It seems that those P electrons are kind of shielded from feeling the nucleus. So they're not real stable out there. And that's exactly why those alkaline earth metals are not at all interested in taking an electron. Is because they really don't have a good spot to put it. Those outer electrons, well, starting a P sublevel is just not very stable. Okay? So now, just one other thing about electron affinity, and that is a bit of an explanation about all three of those, kind of formalizing that. Yeah, one of the interesting things, once again, I'm going to just draw a line through the zero. I like to keep right on, I'm a little bit high. Close though. Notice that nitrogen is right on the zero line. Nitrogen is pretty neutral about gaining an electron. That may be a surprise because nitrogen is a nonmetal. I mean, it's clearly a nonmetal. It's even carbon. Look at carbon. It's pretty into gaining an electron. That's on one side of nitrogen. On the other side of the nitrogen is oxygen. It's good about gaining an electron, but nitrogen's being a party pooper. For the same reason as before. Look at this over here. The electron repulsion. When you add another electron to nitrogen's very stable one electron in each of the two p orbitals, it doesn't want to be messed with so much. It does make a -3 and forms the nitride ion, but putting one electron on a nitrogen is not that much of a slam dunk. I can do this too. See people looking around other people's heads. There's that. Moved it up. Electron affinity is hard. That's the most asked about exercises in the book, is about the electron affinity. Okay, we all good with that? So that's electron affinity. Pretty crazy looking trend on that. We're going to take on now something that's much more reasonable, and that's atomic radius, the size of the atom. This will be the last thing that we'll do today, is talk about atomic radius. Atomic radius is defined, kind of hard to define, it's a funny thing. Because we can't just hold a ruler up to an atom and see how far it is from the nucleus to the outermost electrons. Scientists have to be kind of clever about how they find it. So they can see where nuclei are in atoms. So they normally will use X radiation and take a small sample of a solid, shine an X-ray at it, and then the developing film will pick up where the nuclei were. And so they can kind of extrapolate and see how far apart those nuclei were. And just assume that from one nucleus to the next, if you just cut that in half, that would be the radius of one atom. But just know that atomic radius is the size of the atom. Now, I don't have a graph for atomic radius, but I thought this was even better than a graph. This just shows relative sizes of the atoms. Now, I do want you to know, it's kind of funny in the middle. When you see the transition metal electrons, well, not just the electrons, but the transition metal sizes, there is a little bit of variation here. It seems like, especially in this fifth row, the atoms going to get smaller and then they get bigger. I don't think you're going to have to answer anything about the D block of the periodic table. They'll just ask you about the trend in the S's and the P's. So you can just ignore these D's in the middle. We'll be fine. So what do you notice? You notice across a row, the atomic radius gets smaller. That's what this is